Chemical and biological warfare. We're going to survey in this lecture 3 non-nuclear weapons of mass destruction. Biological agents, which are living self-replicating organisms. Toxins, which are non-self-replicating chemical poisons derived from biological organisms. And chemical agents, which are manufactured chemical poisons. I will not discuss white phosphorus, napalm smoke, or other chemical-based weapons. You can see here the 3 categories of weapons: chemical agents, toxins, and biological agents with various examples. And the grams per target that are needed to incapacitate it. Disease in history. Until the introduction of basic hygiene in the 19th century, armies suffered more casualties from the effects of disease than battlefield losses. In the U.S. Civil War, it was noted that men without beards tended to suffer lower rates of disease. It was eventually determined that this was because people who shave every day incidentally wash their hands at least once a day. Of the 300,000 French soldiers deployed in the Crimean War in the mid-19th century, 11,000 died in combat and 21,000 died of disease. Of the 111,300 British soldiers deployed, 4,774 were killed in battle and 16,000 died from cholera and typhoid. The Russians lost more than 1 million soldiers during the offensive in Crimea. The world population in 1300 was 300 to 400 million people. The Black Death, or the bubonic plague, between 1334 and 1351 killed some 1/4 of the population of Europe and the Middle East, and inflicted lower but substantial losses in East and South Asia, probably killing between 50 and 75 million people. The disease was brought by the Mongols from groundhogs around Mongolia, and was one of the factors facilitating their conquest of the world. The influenza epidemic at the end of the First World War killed 20 million people in 2 years, more than the 17 million that died during the war from 1914 to 1918. About 16 million of those were killed in India and China. AIDS has killed at least 22 million people. You can see here a picture of the influenza epidemic. These are some of the suspected routes that diseases have taken. Most diseases are zoonotic. They begin with animals and human proximity to animals, and then they jump species. So you can see that it was suspected that measles came from Ethiopia and then spread into the Mediterranean. And then the bubonic plague could have come from the Upper Nile, or it could have come from the Ganges, and eventually hitting the Byzantine Empire, and it became termed the Plague of Justinian. The earlier Antonine plague might have been the measles that came from Ethiopia. And you can see the spread of a disease from Persia to China and on into Japan. And you can see malaria spreading from southern China to Shenxi province. The first recorded use of a biological agent was the catapulting of plague victims into the city of Kaffa, now Theodosis in Crimea, in 1346. There are 5 kinds of biological agents. First, Rickettsia. These are lice-borne diseases, such as typhus, scrub typhus, Rocky Mountain spotted fever, Q fever, and 9-mile fever. The second type is bacteria. These are small living organisms. Types include anthrax, bacillary dysentery, undulant fever, cholera, diphtheria, deep fly fever, glanders, Whitemore's disease, salmonella, pulmonary tuberculosis, plague, of which the bubonic variety attacks lymph nodes, pneumonic, septicemic, or sylvatic. In 1979, anthrax escaped from a research facility near Sverdlovsk in the Soviet Union and killed 2,000 city dwellers. Today that city is Yekaterinburg. The third type are viruses. These are self-replicating DNA. It includes prions, which are simple self-replicating protein strands. Types include rinderpest virus, Rift Valley fever, vesicular stomatitis, hog cholera, African swine fever, fowl plague, encephalitis, influenza, yellow fever, dengue fever, hepatitis, Ebola, West Nile virus, camel pox, and hantavirus. The fourth type are fungi. These are complex organisms. Types include Coccidioides immitis, which is producing Sanwikim fever, Histoplasma capsulatum, and Nocardioasteroids. The fifth type are toxins, chemical poisons derived from biological agents like botulism and Staphylococcus. The first recorded use of a biological agent was the catapulting of plague victims into the city of Kaffa, now Feodosis in Crimea, in 1346. There are 5 kinds of biological agents. First, Rickettsia. These are lice-borne diseases, such as typhus, scrub typhus, Rocky Mountain spotted fever, Q fever, and 9-mile fever. The second type is bacteria. These are small living organisms. Types include anthrax, bacillary dysentery, undulant fever, cholera, diphtheria, deep fly fever, glanders, Whitemore's disease, salmonella, pulmonary tuberculosis, plague, of which the bubonic variety attacks lymph nodes, pneumonic, septicemic, or sylvatic. In 1979, anthrax escaped from a research facility near Sverdlovsk in the Soviet Union and killed 2,000 city dwellers. Today that city is Yekaterinburg. The third type are viruses. These are self-replicating DNA. It includes prions, which are simple self-replicating protein strands. Types include rinderpest virus, Rift Valley fever, vesicular stomatitis, hog cholera, African swine fever, fowl plague, encephalitis, influenza, yellow fever, dengue fever, hepatitis, Ebola, West Nile virus, camel pox, and hantavirus. The fourth type are fungi. These are complex organisms. Types include Coccidioides immitis, which is producing Sanwikim fever, Histoplasma capsulatum, and Nocardioasteroids. The fifth type are toxins, chemical poisons derived from biological agents like botulism and Staphylococcus. Modern biological weapons have been targeted on crops and farm animals. Zoonoses, or animal diseases, include anthrax, rabies, psittacosis, rinderpest, swine fever, and brucellosis, which causes animals to abort. For example, you can imagine crop diseases like soybean rust. The U.S. categorizes threats according to 3 categories, A, B, and C. An A category is a high mortality and infectious disease like anthrax, botulism, tularemia plague, smallpox, and hemorrhagic fever. Category B are highly infectious and have moderate mortality like glanders, brucellosis, foot and mouth disease, salmonella, E. coli 157, and cholera. Category C are moderately lethal, requiring genetic engineering for better dissemination, like hantavirus, yellow fever, tick-borne encephalitis. The Soviet Union invested significant research into Lassa fever and Marburg fever. Targets of likely genetic research could be Legionnaire's disease, HIV virus, rabies, and genetically targeted diseases. Now, vaccines normally function as an antibiotic because as a fungus they target the hardened cell walls of plants and bacteria. So taking antibiotics basically is ingesting fungus, and it destroys the outer wall of the bacteria, exposing their innards to the environment and to your immune system. Viruses, on the other hand, are not vulnerable to antibiotics. Here you can see cows killed in a disease outbreak. This is barley infected with rust fungus. This could attack the food supply. This is ergot fungus on corn. Here you have a number of diseases. Pulmonary anthrax is fairly high infectivity. It cannot be transmitted from person to person. Its incubation is 1 to 5 days. It's got very standard symptoms, which makes it difficult to diagnose. The duration of the illness is 3 to 5 days, and there are a number of therapies, including antibiotics. You can see brucellosis, cholera, plague, both pneumonic and bubonic, tularemia, and Q fever. Here, psittacosis, Rocky Mountain spotted fever, epidemic typhus, dengue fever, and eastern equine encephalitis. Here you can see the infection inflicted on an individual by smallpox, one of the most dangerous and infectious diseases that has successfully been eradicated by world cooperation. These are the external manifestations of anthrax and its effects on the brain. This is the external manifestation of the plague, which killed such a large part of the European and Middle Eastern population. Now, the ideal particle size for ingestion into the lungs is 1 to 5 microns, where 1 micron is 1/1000th of a millimeter. And this descends an average of 1.5 meters an hour in the atmosphere, although this varies greatly due to meteorological conditions. Biological weapons dehydrate quickly in low humidity and are susceptible to ultraviolet radiation, in other words, the bright light of the sun. Biological weapons attacks are therefore most likely to be used at night at low altitude. Biological agents can be transmitted via vectors or carriers, such as mosquitoes or fleas on rats, or by aerosol sprays deployed by aircraft, or by weapons in nutrient cakes that dissolve in the environment. Biological agents delivered by explosives or high-impact means normally kill the organisms. Here you can see a typhoid culture. So mosquitoes would be useful for spreading yellow fever, dengue fever, encephalitis, and malaria. Flies could spread typhoid, cholera, and dysentery. Tsetse flies would spread sleeping sickness. Fleas on rats would spread typhus and plague. Lice on rats would spread typhus and trench fever. Ticks and mites from rats would spread Rocky Mountain fever, tularemia, and Colorado fever. There are 200 viruses that are transmitted by blood-sucking arthropods like mosquitoes, of which 75 produce diseases in humans. Here you can see Soviet troops, or it could be French troops. Yeah, these are in fact French troops in biological chemical weapons outfits. Here's a mosquito sucking blood out of a human. This is a tick, argacid. Here you can see a harvest mite, a plague flea, and a fever tick that could live on the surface of a brown rat and then jump onto a human. Now, biological weapons are potentially the most weight effective because they can expand their mass through reproduction, whereas chemicals and toxins cannot. You can see in this picture the estimated fatalities from 50 kilograms of a biological agent to drop from 2 kilometers upwind of 500,000 people. So biological weapons can be distributed as a cocktail or mixture of multiple diseases. So you can see how many casualties there would occur and the proportion of them that would be fatalities. Look particularly at anthrax, in which the majority of those infected would be killed. Now, biological weapons also have varying incubation times, the period after ingestion that they begin to attack a host, and therefore are difficult to use in battle. Biological agents are also susceptible to environmental conditions and may lose their virulence even though they can continue to survive. Counterweapons to these are pesticides and insecticides. The problem with living biological weapons is that it's very difficult to use them and then ensure that they don't get back and infect friendly soldiers. Even if all soldiers and members of a population could be immunized, diseases can mutate into strains resistant to the current antibodies. Here you have an aircraft spraying defoliant during the Vietnam War. The obvious problem is that humans are immunologically naive. Blanket immunity injections themselves may produce a small percentage of fatalities, though at a far lower rate. The U.S. had inoculated 150,000 of its soldiers against anthrax during the 1990-1991 U.S.-Iraq War. Human immune systems vary a lot, and it is unlikely that a disease will be found that will kill all humans, as the disease gradually provokes immunities in humans, though they may remain carriers. With the exception of the World Health Organization's campaign to eradicate smallpox virus, diseases are very hard to eliminate, and the smallpox was eliminated in 1979. Here you can see British soldiers in a trench with gas masks during the First World War. Basic laboratory skills and understandings of pathology is all you need for a biological weapons program. In biological warfare, it seems easier to produce biological agents than it is to come up with antibodies. The British developed anthrax as their principal deterrent weapon against German chemical agents. It was chosen because the spores can survive in the ground and water indefinitely, and it is resistant to sunlight for many days. Here you can see a Soviet TMS-65 decontamination for armored fighting vehicles. The problem is that chemical weapons can get into the paint, and so you need to use a significant heat to burn off the chemical agent from the surface of armored vehicles. Now, the Germans in the 1920s and 30s, specifically one scientist, I.G. Farben, developed nerve gases to kill humans for the German state. Now, in the First World War, he contributed to chemical weapons research that enabled the Germans to begin the use of chemical weapons on the battlefield. He was from a Jewish family, and his wife was not happy with his decision to help the German state to develop chemical weapons, and so she committed suicide in protest. He did not even go to look at her body, and instead he went to the Eastern Front to test his chemical weapons program against the Russians. He continued to do research throughout the war as a committed German nationalist. But with the rise of the Nazis, Hitler made it very clear that he wanted to protect I.G. Farben so that he could continue his research. But the continuous arrest of his close Jewish colleagues and workers in his lab resulted in him finally resigning to the fact that he could not stay in Nazi Germany. And as a broken German nationalist, he fled to Switzerland and subsequently died. So this is the effects of anthrax on a hand, and the picture's not very clear, but it's essentially the immune system reacting to the toxin's effects on the surface. We have inside us a lymphatic system, which is the prior circulatory system we had before we had blood and a heart. And within that we have a bright yellow liquid, lymphatic fluid, which carries a part of the immune system to protect us. So here, this is a reaction to poison ivy, and what you can see is the poison ivy's toxins having penetrated deep into the skin because of the open pores. The body has reacted, and you have the entire surface of the skin red, because what's happening under the skin is the lymphatic nodes are injecting liquid with various biological chemicals to deal with cleaning out and counteracting the poison ivy toxin. So here you can see large, relatively hard blisters, and the yellow liquid is what happens when they burst spontaneously. And that yellow liquid is not modified in any way. This is the true color of the liquid, and it's the lymphatic liquid that you have. And typically the limbs will grow up to twice their size as the body accumulates fluid in order to feed into the lymphatic system, depending on how broad the infestation is. So here you can see the burst of the blisters on the arm, and basically begins to look like bubble wrap. Basically, the entire surface of the skin is covered with blisters on top of blisters, and sometimes those blisters explode, leaving the lymphatic liquid, and you have scars left over that can bleed if there's too much exposure of the skin under the blister. Now, this is again the true color of the skin. As the toxin of the poison ivy spreads, the skin becomes bright red, and you can see faintly that virtually the entire surface of the skin is covered in blisters. Some of them are very large, most are very small, and it's extremely irritating. This is what happened to me. These are my arms and my legs when I got a full body exposure to a rather extended interaction with poison ivy, and it ultimately required weeks of recovery, and scars remained on my limbs for months, and I had to take steroids, cortisone, as well as surface antibiotics, and antibiotics because the skin the bursting skin is effectively exposed to external bacteria as a consequence. But these blisters are not caused by the poison ivy. It's the body's reaction to try to isolate the poison and expel it from the body. This is Guinard Island, where the British tested their anthrax bombs during the Second World War. This was their equivalent of a nuclear deterrent, and the British plan was to drop them over farming areas in Germany and then infect the food supply and the German population themselves. These are the facilities at Porton Down where British and Canadian scientists worked on the development, the testing, and the mass manufacture of anthrax, and essentially the weaponization of England's biological weapon in order to counteract any German use of nerve gas on British cities. The Japanese also engaged in biological weapons research. The Pingfan region of China contained 18 establishments, each with about 300 scientists and workers conducting biological experiments. The Japanese could grow about 500 million plague-infected fleas per year. The disease of interest for the Japanese was typhus, cholera, tetanus, typhoid, smallpox, tularemia, glanders, and gas gangrene. Now, the one exception during World War II was that the Japanese, who used both gas and biological weapons in their war against China. Units 100 and 731 conducted unconscious vivisections, that means cutting people apart while they're still alive, on Chinese subjects. They infected a village of 5,000 persons with the plague in a large-scale controlled epidemiological experiment at Changchun. Here's a letter from Major Ishii Shiro, initiator of the Japanese research program in China for biological advancement of weapons, to his superiors in late 1932. Quote, "Due to your great help, we've already achieved a great deal in our bacteria research. It is time we start experiment. We appeal to be sent to Manchukuo to develop new weapons." Close quote. So here you can see Unit 731, this complex at Pingfan, China. The Japanese biological weapons effects is being evaluated on a captive experimental victim, and you can see a Japanese autopsy of a dead experimental victim. This is a banquet of Japanese doctors from Unit 731 during the China War. In exchange for information to the Americans on biological weapons, none were prosecuted, and the vast majority concluded their careers as heads of hospitals in Japan without ever being prosecuted for war crimes. Now, the Japanese were probably intending to use biological weapons when they sent balloons to deter the U.S. strategic bombing of Japanese cities. Here's the U.S. identifying a balloon and a civil defense NBCW suits that civilians can wear. The Japanese also tested their biological weapons on Russian prisoners of war and other European prisoners of war. Now, the Soviet Union during the Cold War had a much larger program than the Japanese. They employed 60,000 workers in 50 locations across the Soviet Union engaged in biological weapons research. It was very extensive. The U.S. also had biological and chemical weapons research facilities, including Fort Detrick. The U.S. was mostly interested in countering biological weapons. Here you can see a picture of the Ebola virus strain. Now, toxin history. The first recorded use of a toxin weapon was in 600 BC by Solon at the Athenian siege of Kira, in which the besieged drinking water was poisoned with the poisonous Helleborus plant, inducing disabling diarrhea and contributing to the surrender of the city. Here you can see ricin toxin, saxitoxin, enterotoxin, and tetrodotoxin. Now, botulinus toxin, of course, is used in cosmetics because it essentially paralyzes the facial nerves. Now, toxins are generally considered safer because there is no epidemiological risk in the sense that they can't spread. And they can't spread back to the attacker. Here you can see botulinus toxin in a container, and you can see the nightshade poison which attacks the nervous system from this berry. Chemical weapons history. The first recorded use of chemical agent was by the Spartans during the Peloponnesian War, but they were harassing rather than a lethal agent. Lethal chemical weapons were first used on April 22, 1915 by the Germans against 2 French divisions of colonial troops. 177 tons of chlorine gas were released across a 6-kilometer front, inflicting severe local damage on unprotected forces. On April 24th, the Germans gassed the Canadians. Non-lethal gases had been used by the Germans and French against each other and against the Russians in 1914 and 1950. Chemical weapons were used extensively in the First World War. In 1917, in the First World War, 15% of all British casualties were caused by gas, and only 15% of those were actually killed. Intensive German use of gas in the last 18 months of the war actually increased the proportion of losses to 18%, which is a more realistic figure for contemporary use. U.S. soldiers who were less well prepared in terms of experience, training, and equipment suffered 70,752 casualties, including 1,500 deaths, or 27.4% of all the casualties they suffered during the First World War. By the end of the First World War, 25% of all artillery shells were used to deliver chemical agents. In World War I, there were deployed 124,000 tons of gases, causing 1,296,000 casualties. 4.6 of the total casualties suffered in the war, of which 91,000 were fatal. So in effect, it took 1 ton to wound 10.5 persons, and 1 ton would kill 3/4 of a person. The British used, or allegedly, were accused of using gas to suppress a 1920 Shia uprising in Iraq, but it seems that these were exaggerated. The British did consider using gas against the Pashtun in Afghanistan and against the Iraqis, but in both cases, political pressure was applied not to use the weapon. Here you can see a machine gun crew in a chemical outfit. Here's the terrible environment of British soldiers and Germans fighting with chemical weapons. Here you can see gas being released in the advance of the soldiers. And these are soldiers lined up having been blinded by gas. Now there are 6 types of chemical agents. The first are vomiting agents, lacrimators. This is irritant agent. They tend to be non-lethal, like tear gas, CS, CN, CNCS, CNB, BBC, Adamsite, and BZ. The second type is nettle gas. This is a skin irritant agent. It's usually non-lethal, like dichlorophoromoxine. The third type is choking gas. This destroys the delicate lung tissue that extracts oxygen from the air, killing through asphyxiation. It caused 80% of the casualties in the First World War. Its main type was phosgene. Phosgene was considered the most effective in the First World War because it took effect without detection. The fourth type is blister or vesicant liquid sprays. These damage the eye, the skin, the lung, and if ingested, the intestinal tissue through chemical burns. It corrodes equipment and it rots clothing. Types include lewisite, mustard, and chlorine gas. The fifth type are blood agents. These attacks the enzyme cytochrome oxidase. It replaces oxygen in the bloodstream, leading to blood poisoning, including brain death. Types include cyanogen chloride, hydrogen cyanide, and arsine. Nerve gases include fortified pesticides. It shuts down the nervous system, inducing a heart attack. Nerve gases attack chemical enzyme acetylcholinesterase that shut off nerve impulses. This causes the nervous system to burn itself out within 15 minutes and then poisons the body, ultimately inhibiting the transmission of voluntary and autonomic nervous signals. Types include sarin, tabun, and soman, which are nerve agents developed in World War II by Fritz Haber. And modern versions are VE, VG, VS, and VX. In 1960, a VX leak from a plant near Newport, Indiana, killed 6,000 sheep. So here you can see some of the different agents: tabun, sarin, soman, and VX. The first aid medical solution, distilled mustard or nitrogen mustard gas, phosgene, CN, DM, CS, and BZ. So chemical and biological agents tend to have a short persistence in extremely hot climates, particularly in deserts in which ultraviolet radiation breaks down the compounds, and in jungles where the heat breaks them down. Very cold temperatures also render chemical and biological weapons less effective by condensing vapors that would otherwise spread. But when soldiers move into warmer areas, for example, like inside a tent, then the agent can be regaining their potency and kill. Sunlight reduces the effectiveness of nerve gases by up to 60%. The ideal condition for a chemical attack is a stable, rainless, overcast weather with a 5 to 10 kilometer wind between 10 and 25 degrees Celsius, with a temperature inversion in which warm air is trapped between a colder surface and belt of cold, high-altitude air. The ideal terrain is flat, as cities and mountainous areas create powerful air currents. This here is the chemical compound for mustard gas. Now, the body has a natural mechanism to detoxify poisons, but generally fails catastrophically when overwhelmed. Well-trained soldiers with chemical protection equipment can reduce their daily losses during chemical attacks to 2% per day. Gas masks are filled with a small charcoal grain, each with a deep tunnel that traps passing gas. 1 gram of charcoal has a surface area of 334 square meters if you unwrap it and make it flat. Chemical protection gear must be replaced frequently, especially the charcoal filters that quickly end up getting used and filled with gas. Chemicals are easily neutralized by alkaline chemicals such as soap. Many combat vehicles also have internal filters that seal them from a chemical threat from the outside, but the duration that soldiers remain within the vehicle is limited. The Maginot Line was designed as chemically resistant. The standard military drill is to remain outside of contaminated areas. Again, you can see here the picture of the TMS-65 decontamination of a platoon of Soviet tanks. Atropine injections can lead to severe shock if the individual is not infected by an actual nerve agent. But under normal circumstances, after having been affected by a nerve agent, these would be stabbed into a leg, and there would be a spring-loaded needle that would then inject the atropine into the thigh of the user. Here you can see it being used. During peacetime, this would be practice, and a saline solution would be used. During the Cold War, we carried around a small detector that picked up the chemical, biological, and nuclear agents in our environment, and these were periodically replaced. So protective gear is very cumbersome because it's heavy and it gets very hot inside, especially when you have to wear it when it's 30 to 40 degrees outside. Although it's quite comfortable in the winter. So you can see that if you're doing heavy work like digging a trench, your work output is going to collapse in an hour and 20 minutes. If you're doing light work, which is operating a radio, you can pretty much operate indefinitely, although at significantly lower capacity. So fighting in this kind of gear is very difficult, and normally what you do is you'd use this to get through an area that was infected, but then you would quickly pass through it to be able to get your equipment off. It was estimated that soldiers would go through an outfit per day. in these environments, which is really not realistic. The supply would run out fairly quickly. So morale is expected to plummet if protection equipment fails. I can tell you from having spent a lot of training in these outfits during the Cold War that it's difficult to communicate to people because everyone looks the same. You don't know who is who, you don't know who the boss is, and it's very difficult to communicate. You're basically yelling at each other all the time, and it's very hot, and your vision is very narrow. And pooping or drinking is difficult, and your entire body is covered in sweat and water is filling up and you can't scratch your nose. It's extremely irritating. Now, some of the symptoms of chemical weapons is anxiety and headaches and nausea, and these are associated with both chemical weapons and just anxiety in general that you might be infected with chemical weapons. So it's very difficult to diagnose if someone has been affected by chemical agents. You can see here Soviets in their variety of chemical weapon suits and Americans in their variety of 1980s nuclear biological chemical weapon suits. These are improvised gas masks during the First World War, essentially motorcycle goggles and urine-filled gauze. Now, chemicals kill people, animals, and plants, but they leave physical structures, including airfields, bridges, and factories intact. Chemical weapons, both of a persistent and non-persistent nature, can be designed to be lasting for several days or indefinitely until the environment cleans it up. And so it can dissipate after an initial attack, allowing friendly troops to pass through. Chemical attacks usually consist of chemical, high explosive, and fragmentary shells being used in conjunction. A small hole created by a fragment in a chemical protection suit would expose someone to the agent. Chemical weapons significantly slow down military operations. Here you can see a list of herbicides and defoliants, many of which were used by the U.S. during the Vietnam War. Here you can see 4 U.S. aircraft spraying defoliant over the jungle in Vietnam. This is a U.S. MLRS chemical weapon launcher, which can launch chemical weapons on the Soviets. The U.S. had nerve gases of a binary nature, which when the 2 compounds were mixed, became lethal. These are an assortment of Soviet-era chemical weapons bombs that would be dropped from aircraft. Now, chemical weapons can be unpredictable because it can be carried by unpredictable winds. Chemical weapons are typically used against fixed targets like airfields, supply depots, large command complexes, port facilities, bridges, and against fixed group concentrations. Planned massive Soviet use of chemical weapons against NATO airfields and other installations during the initial attack of the Third World War into Europe was expected. My Danish military colleagues indicated to me that they expected hundreds of thousands of casualties, as the Soviets would have nerve-gassed most of the Danish airfields in the Baltic. Chemical weapons pose little threat to airborne pilots or ships at sea because of the wind and the corrosive effect of seawater. However, ground crews and grounded pilots are very vulnerable, and it's been estimated that ground crews maintaining aircraft and a pilot flying their aircraft operate at 50% effectiveness when wearing a chemical protection suit. Small concentrations of nerve agents, while non-lethal, may lead to blurred vision and disorientation and may endanger the ability of a pilot to operate their aircraft. During the First World War, losses were as such. Prepared and advancing attackers into a gassed enemy position suffered about 10 to 15% casualties. So even if you had soldiers that were fully trained and prepared and rehearsed, and then you gassed an enemy trench and then your troops advanced into it, you would suffer a high level of loss. And if you were to do this attack over and over again, your unit would become ineffective in about 5 days. An unprepared defender could suffer up to 60% casualties. Now, these are some of the contemporary estimated casualty losses for a mixed chemical and conventional shelling. Prepared troops would suffer between 10 and 30% casualties. Fatigued or underprepared troops would suffer 40 to 50% casualties, and untrained troops would suffer 80% casualties. The Soviets assumed that an attacking unit gas using gas would suffer about 20% losses per day and when reduced to 30% of its strength, after 5 days would be rotated out of the line to be reconstituted by reinforcements. Most gases are heavier than air and thus find their way into valleys, trenches, and underground bunkers. Here you can see a medevac procedure for someone who's been affected by NBCW. Now, chemical weapons use did involve British use against the Bolsheviks in Russia until 1921, the Italians against the Ethiopians in 1935, the Germans against the Russian in caves in Crimea in 1942, although those were non-lethal, the Egyptians in Yemen in 1961 and 1967, primarily phosgene gas, the Vietnamese in Cambodia and Laos in the 1980s, the Soviets against the Afghans, although that seems more like it was poisons used in wells to deny water to the Mujahideen in the villages, and by both sides in the Iran-Iraq War between 1980 and 1988. There was frequent mention in the media that the British used it against the Kurds and against the Afghans, but there is actually no evidence that this is true. So let's take a look at the case of the Iran-Iraq War in 1980-1988. By 1988, Iraq's production capacity was 70 tons a month of mustard gas and 6 tons months each of sarin and taboo nerve gases. Iran was catching up by the end of the war, but was limited mainly to mustard, phosgene, and hydrogen cyanide gas. Iraq's first use of chemical weapons were defensive after Iran had begun its counterattack into Iraq. Iran made its first use of chemical weapons in 1984 or 1985. On February 26, 1988, Iraq, with mustard gas, killed about 5,000 Kurds out of 60,000 that were casualties while fighting over the town of Halabja. There was an allegation that Iran had used hydrogen cyanide in the same attack, which was later disproven. Now, Iran claimed that Iraq inflicted a total of 25,000 casualties, including 260 deaths, until April 1988. Iraq inflicted a further 20,000 gas casualties in the remaining 3 months of the war. Iraq inflicted at least 5,000 deaths on the Kurds. Here you can see a French biological chemical weapons suit. Here is the map of where the conflict occurred, and most of the gassing occurred along their common border. Now, the strategic use of chemical and biological weapons could inflict large casualties because it could be targeted against civilians who were less well prepared than military personnel. Although gas bombs were available by both the Allies and the Germans in World War I, the threat of retaliation seems to have deterred their use against civilian targets. But of course, we're not entirely sure. Most major European powers developed bombers and gas weapons, but when the Second World War broke out, the British made their declaration of war with an official request for Germany's confirmation of a biological and 1925 chemical weapons conventions. It was also proposed that the League of Nations take control of all bombers and use them to enforce world peace, and these Germany confirmed that they would not use biological chemical weapons. The British and Germans deterred each other and therefore never made use of their arsenals. Here you can see a Soviet soldier in his outfit. Now, Hitler was relatively ruthless. Now, he had been gassed and blinded during the First World War, although some dispute whether that occurred, and he experienced the collapse of Germany in 1918, suggesting that he did not think that Germany would survive a chemical attack on its cities. There's also evidence that the Germans believed that the British had developed nerve agents as well. On December 2nd, 1943, after a German bomber raid hit a U.S. cargo ship, the SS John Harvey, carrying 100 tons of HD-type mustard gas in 2,000 M47A1 bombs in the Italian harbor of Bari in the south of Italy, released the agent, producing 617 casualties, including 83 deaths. There's actually an Italian government film that was declassified that shows the American soldiers pulling bodies out of the harbor that had been killed by the gas. On December 3rd, 1984, the Union Carbide cotton pesticide plant at Bhopal, India, released 42 tons of the deadly gas methyl isocyanate that killed 2,500 people and injured 200,000, of which 50,000 continue to suffer chronic injuries. Aum Shinrikyo, a terrorist group from Japan, used sarin in their March 20th, 1995 attack on the Tokyo subway, killing 10 individuals and injuring 5,500 commuters, and they used hydrogen cyanide on 2 other occasions with less success. Now, chemical weapons are easily produced by any state with chemists and a rudimentary chemical manufacturing capability. The U.S. did research into using lysergic acid, LSD, as a disorienting agent, but an antidote was found, so the research was discontinued. Some of that research was done covertly on mental health patients at Ravenscraig in Montreal. Many chemical weapons were left by the Allies at the end of the Second World War, including in India and Pakistan. One of my instructors when I was an Army engineer, and Army engineers are responsible for removing EOD, explosive ordnance disposal, basically blowing up old bombs, were clearing First Nations land in the prairies, and they came across an unrecognized, unexploded artillery shell. And so they placed an explosive charge next to it and set it off, and this set off a blue gas. And everyone dropped everything they did, and they ran off in different directions. And it's clear this was an unexploded gas bomb from the First World War that had basically been sitting in the ground for 2/3 of a century. A difficult problem with chemical weapons is that they're difficult to store. Because they're corrosive, military shells filled with them degrade quickly. The U.S. has developed binary chemical weapons that are not lethal until two separate chemicals are used in the same shell. For example, you have methylphosphanol difluoride and isopropanol, and this leads to 70% Gb and a 30% hydrogen fluoride. Another type is ethyl 2-diisoprolenethyl methylphosphonate and dimethyl polysulfonate, NM, which leads to VX nerve gas. So in terms of stockpiles, the Germans started World War II with 2,900 tons of chemical agents, but no means of delivery as Hitler forbade it. The Germans produced 12,000 tons of Tabun nerve gas out of their total arsenal of 62,000 tons of chemical agents. Between July of 1940 and December of 1941, the British were able to increase their stockpile from 410 to 15,262 tons of mustard, phosgene, and other gases. Churchill considered using them against German cities in response to the V1 and V2 attacks, but was overruled by the chiefs of staff. In the Second World War, the U.S. stockpiled 135,000 tons of chemical agents, more than that used during the First World War by all states. The U.S. deployed in England another 10,000 tons of phosgene gas with them. The U.S. Army was vetoed in its use of chemical weapons at Iwo Jima against the Japanese. Now, the British had cancelled the program to produce calcium to methyl chloride to kill root crops, and the U.S. had considered spraying Japanese rice crops with ammonium thiocyanate. U.S. chemical weapons during the Cold War were mainly sarin, of which there were 18,000 tons, and VX nerve gas, of which there are 4,500 tons, mostly stored in the U.S. and Europe, out of a total amount of 42,000 tons of chemical agents. The U.S. had 4,700 soldiers tasked in chemical warfare and 700,000 dedicated chemical missiles and artillery shells. The Soviet Union, by contrast, had accumulated 350,000 tons of chemicals, more than the chemicals that had been accumulated during both the First and Second World Wars, and the Soviet Union had 100,000 workers dedicated to chemical warfare. Shinrikyo, the Japanese terrorist group, had amassed enough materials to manufacture 5.6 tons of sarin nerve gas.